I'll discuss work that I've done with colleagues on constraining the shear and the bulk viscosity of QCD using measurements from both RIC and the LHC. Now, as always, feel free to ask questions during the talk if it's easier and if it's going too fast, or if there's anything that's too straightforward for you, just let me know and I can adjust the speed. Now, I think everybody's familiar with the idea that fluids have viscosities, and that this viscosity is a characteristic property of the fluid. So, for example, water has a certain viscosity. Helium will have a certain viscosity. And of course, if you have a plasma of pions, or if you have a plasma of quarks and gluons, this plasma will have viscosity as well. And in all these different cases, your viscosity is a reflection of the underlying interaction between your microscopic degrees of freedom. So for water, your viscosity will be a reflection of the electromagnetic interactions between the H2O molecules. Same for heliums. And in a nuclear plasma, your viscosity will be a reflection of your interactions between pions, for example, or your interactions between quarks and gluons. So the reason we're interested in the viscosities of QCD, it's that it's an emergent property of QCD. It's an emergent property of how these microscopic interaction, how all these different degrees of freedom interact with each other, and how collectively they produce this viscosity. Now, I'll be saying viscosity throughout this talk, I will always mean either the shear viscosity to entropy density ratio or the bulk viscosity to entropy density ratio. So we always normalize by the entropy density. So eta over S or zeta over S. So these three were shear viscosities. Now, the two things that I can say quickly to summarize why we're interested in viscosities and what they mean. So viscosities are a macroscopic property of the fluid. And by macroscopic, we mean a long distance and long time property. And I want to emphasize this because obviously when we'll be studying heavy ion collision and using fluid dynamics to study heavy ion collisions, we're not saying that the entire collision can be described with hydrodynamics. We're saying that certain parts of it and certain features of the collision can be described with hydrodynamics. From this, we can study the viscosity. But of course, there will always be parts of the heavy ion collision that have nothing to do with hydrodynamics. The viscosity, you can think of it as characterizing how the fluid responds to deviation from equilibrium. So fluid dynamics in general assumes that your medium is locally close to local thermal equilibrium. And viscosity will characterize how the fluid responds to deviation from equilibrium. And if you want a simpler way of thinking about this, just take a perfectly equilibrated plasma of quarks and gluons and just perturb it in a specific way. Now, this perturbation will dissipate, and viscosity is a characteristic way that the fluid responds to this perturbation and how it goes back to equilibrium. Now, because it's a property with respect to an equilibrium state, it means that depending on where you are in your phase diagram, you expect your viscosity to be different. So if I was showing here a simplified phase diagram for water, and what you can do is plot this shear viscosity to entropy density ratio, this eta over S. You can plot it for different trajectories in your phase diagram. And you can see that depending on where you are in your phase diagram, you can have significantly different viscosities. So again, it's a departure from equilibrium. So it matters what your equilibrium is. And here you can see this jump. So whether you have a jump or not, so this dashed line corresponds roughly to this trajectory here, where you have where you don't cross any phase transition. But this line here, the black one, is at the lower, the solid one is at a lower pressure. And in that case, you actually do cross you do have a phase transition. And this phase transition caused this change in the viscosity. And we have the same thing, obviously, for nuclear plasma. So a nuclear plasma has a phase diagram. Typically, we'll call this the phase diagram of QCD. And you'll have a different viscosity across this phase diagram. Now, this phase diagram itself is something that is being actively studied. And there's a lot that we know about it, and there's still a lot that we're learning about it. Here, I'm showing the phase diagram as a function of two conserved quantity, the energy, so the temperature that corresponds to conservation of energy, and the baryon chemical potential that corresponds to the conservation of baryon number. And at low baryon chemical potential, we actually know a lot about the phase diagram from lattice QCD or from different effective models that we have, like the hadron resonance gas. And all across this phase diagram, there's some information that we know from other calculation or other measurements. Now in this talk, I will really restrict myself to a specific region of the phase diagram, which is at 0 baryon chemical potential here, which is in part because that's a region where we already understand the phase diagram quite well. So it makes sense to study the next near equilibrium property, which is the viscosities. The other reason is that this is a region of the phase diagram that can be studied at mid-rapidity at RIC and at the LHC. And we can just think of, the baryon chemical potential is small because if you look at the number of baryons and anti-baryons produced in most high energy gold-gold collision at RIC, and also all collision at the LHC, you get roughly the same number of baryons and anti-baryons. Now, what I'm going to describe is an attempt, in a sense, to measure the viscosity of a nuclear plasma, the viscosity of QCD, using heavy ion collisions. Now, of course, we'd also like to be able to calculate it from first principles and to compare. Now, the reason that we want to do both, right? So those are not exclusive in any way. Now, the viscosity is quite difficult to calculate from first principle. I put here this recent paper that Guy Moore wrote that has, I think, a very clear title: Shear Viscosity in QCD and Why It's Hard to Calculate. And it's not that we don't know anything about the viscosity of QCD, a shear or ball viscosity of QCD from first principle, but we know it in very specific regions of the phase diagram. If you go at low enough temperature, so if you really have a gas of baryons, there's an ensemble of calculation that calculated the shear and the ball viscosity. If you go at extremely high temperature, much higher than the ones shown in this axis, you can use perturbative methods, and you can compute the viscosity from a weakly coupled quark-gluon plasma. Now, the region of temperature that we have access to in heavy ion collision is closer to here. It's around 150, 200, 300, 400 MeV. And it's a very interesting region because that's where we have deconfinement from hadronic degrees of freedom to collared, either quarks or gluon, or just think of it as a collared plasma, a strongly coupled deconfined plasma. And this transition happens around 150 MeV, 160 MeV. And it's a very interesting region of QCD. And it's also a region that is especially difficult to study from first principles. So we don't have very many calculations of the shear viscosity here. And maybe you're wondering what these calculations are. So this black line here was a perturbative calculation that at leading order, assuming a weakly coupled quark-gluon plasma. And it's technically only valid at much higher temperature than this, not even 1 GeV or 10 GeV. Most likely you have to go to temperature of 1 TeV for that kind of calculation to be valid, or at least to be precise. You also have some calculation at lower temperature that uses gases of baryons or gases of hadrons, but really this region is difficult to evaluate from first principles. And there's ongoing work, and hopefully people will be able to do it as well. And in the meantime, what we want to do is constrain it from measurements so that we can eventually compare what we extract from heavy ion collision to those calculations. So how do we constrain the viscosities using heavy ion collisions? This is a schematic description of a heavy ion collision, where you start with the nuclei, which are accelerated at extremely high energy. So you have ultra-relativistic heavy ion collisions. And the two nuclei collide. And after a short amount of time, after about 1 Fermi of evolution, you have the formation of a plasma of strongly interacting deconfined nuclear matter. So you can call it the strongly coupled quark-gluon plasma if you want. And this plasma will expand, dilute, and when it's sufficiently dilute, it cannot remain deconfined. So it reconfines into hadrons, and eventually those hadrons will fly out and be picked up by detectors like Alice, STAR, and others. Now, all of this happens, of course, on a very short time scale of the order of, so the end of the plasma phase is probably before 10 to 15 Fermi. So you're talking about 10 to minus 23 seconds. And it's really in this phase here that you have this connection, that you're describing this phase with fluid dynamics. So it's in this phase that you have the connection between the heavy ion collision and the equilibrium and near equilibrium properties of QCD. So it's really through here, through this phase, that you can constrain the viscosity. The challenge is, of course, that you can't see this phase in a heavy ion collision. You have control over the kind of collision that you do and the energy of these collisions. But what you see at the end is this jet of just all these hadrons that are being picked up by the detectors. And you have to reconstruct, you need a model that describes from beginning to end the collision so that you can really access the shear viscosity and the ball viscosity here. Let me just confirm, can you see when I move my mouse?
Yeah,
we can.
Is it easier? Maybe I'll use it. Maybe laser pointer is easier. Let me try this.
That's even better.
Okay, so good. So we can make some simulation. I can show what a real life simulation of a collision like this looks like. So here what I'm plotting, so this axis is time here, just like it was on this axis. This axis is transverse direction, just like it was here. So transverse direction is that you cut your plasma transverse to collision axis. And I'm plotting here the energy density. And typically, you may be more used to see plots of the temperature when you look at this. The benefit of plotting the energy density is that it's always well-defined, no matter whether you're in equilibrium or out of equilibrium. So you can plot at earlier time and still have a well-defined energy density. And what you can see, so what I showed in these different colored regions, so I found the energy density that correspond to a temperature of 150 MeV, which is the deconfinement, roughly the deconfinement temperature of QCD. And I found the energy density that correspond to 200 MeV, which is, again, you can debate on the exact number, but you can define 150 to 200 MeV as the deconfinement region of QCD, because it's not a phase transition, it's a crossover. So you have a window where you go from confined to deconfined degrees of freedom. And so this region between 0.3 GeV per Fermi cube and 2 GeV per Fermi cubed is this grayed out region. So this is a gold-gold collision at Rig. And you can see that actually you do have regions of high temperature, high energy density, but you also have a large region of, in a sense, temperature or energy density that are in a crossover region. So what we hope in heavy ion collisions is that we can constrain the viscosity, hopefully at high temperature, but at the very least in this deconfinement region between 100 to 200, 300 MeV. Now, the way we constrain viscosity is relatively straightforward. You have this model that describes the collision from beginning to end. You change your viscosity. As you change your viscosity, you're changing the expansion of your plasma. And when you change the expansion of your plasma, you change the number of pions, the energy of pions, number of protons. You change the hadronic distribution that is being picked up by your detectors, that it's being measured at the end. So you're changing the observables by changing the viscosity. And what you want to do is simply to tune this viscosity so that you describe as well as possible the largest number of measurements possible. Now it's well known that—
Can I have a question there? Sorry.
Sure.
On the previous slide. So why is this not symmetric across the y-axis?
It's not symmetric because, so you mean y is like -5 different from 5?
Yeah.
It's only fluctuation. So this is a single event, actually.
Oh, that's a single event. I thought this was like sort of averaged over events. Okay.
No, so it's interesting because even if you start with a large amount of fluctuation initially, which you can't really see so well, I have a different picture on a log scale. I can show you at the end if you want. And even if you start with a large number of fluctuation, a large amount of fluctuation initially, it gets damped relatively quickly, and viscosity also helps damp it. So that, as you can see, for a single event at freeze out, you already have a pretty symmetric distribution, even if you started with something highly asymmetric. So that, I mean, highly asymmetric on average, right? So you have a fluctuation, but you have some underlying structure that leads to this symmetry.
Yeah, thanks.
So may I ask another question regarding like this one? So in the table that you listed, like the temperature to the energy density correspondence, it's quite surprising, at least to me, that you increase like 50 MeV in temperature, and then your energy density almost increases by like another of magnitude. So, and you just said it's like the same region of QCT crossover. So is that like how it goes generally, or is there like something special about this temperature region?
So here they show, so it changes more quickly in this region actually. So that's in a sense the definition of that's a sign of deconfinement. That if you plot this E over T forward, it's relatively constant at higher temperature, and at lower temperature it's also relatively constant. But in this transition, you have this quick transition from having, in a sense, just hadron degrees of freedom, and here you have all these quarks and gluon degrees of freedom. So you can really see from 150, you have 4 here, to 200, you're already at 8 here. So you already have this, you already have this change in normalization that's about a factor of 2. Then you also have the fact that it's a T4 power.
Okay, there's another. Okay, I omitted that when I was doing the calculation. Okay, thank you. So yeah, this is like changing pretty dramatically. Thank you.
Yeah. Any other question at this point?
Well, this is going backwards a little bit. The timescales in the pre-equilibrium phase must make a difference, I presume, in, as you say in this slide, right? It's a pre-equilibrium phase, and then maybe this is something you're going to answer you know, what sort of differences are there within the range of our knowledge of what's going on, you know, in the early stages? And then how does one pin down what's going on in the early stages?
Right. I'll come back to this later. Really, in a few slides, I'll show that everything that's before the hydrodynamics, which we call the pre-hydrodynamics phase, or the initial condition of hydrodynamics, there's a lot of uncertainty there. And at the moment, there are different ways of addressing it. But either you choose your favorite microscopic model, which will have some description of what happens at early time, but may not exactly match what happens in heavy ion collision. Or what we did is to use a very flexible model where you allow this transition time to vary. So this pre-equilibrium time to vary in a wide window, and you allow essentially the initial condition of hydrodynamics to vary a lot. And you have some constraint when you compare with hydrodynamic measurement. You end up with some constraint, but I think really the answer is, if you want to know what's happening at the earliest stage, hadrons will probably not answer that question. They're not the ideal probe. Probes like jets or probes like photons or dileptons will be much better at this. And I'll come back to this later. Yeah.
Okay, thanks.
All right, so as I was saying, the viscosity, you change the viscosity, you look at how it changed your observables, your number of hadrons, the momentum distribution of those hadrons, and then you can see how much each observable depends on the viscosity. And very early on, it was realized that certain observables were very sensitive to the viscosity. This is one of them. This is one of the pioneering paper by Matt Lusum and Paul Romachki, where they showed that if you look at the hadronic V2, which is in a sense how many hadrons are produced in one direction, as opposed to how many hadrons are produced in the other direction, which would be coming out of the screen. You compare this, and this is a sense an anisotropy factor for your number of hadrons coming in these two different directions. And the viscosity tends to even out those differences. So even if you have differences at early time, it tends to even them out. So it has a large effect on this V2 observable, on this momentum anisotropy observable. And so it looks from this figure that you could already almost answer the question, right? That, well, the data this was early V2 data, but data is in this ballpark. So et al. Rest should be around 0.08, or maybe a little smaller. There's a few things to unpack here. The first thing being that this was an early simulation, and of course, they were working under simplifying assumption. One of them being that your viscosity is your et al. Rest is a constant. Now we know that's not the case. Et al. Rest is not a constant. It's a function of temperature, as I showed earlier. And this is an important point. It's that it's extremely difficult to constrain because you're trying to constrain an entire function as a function of temperature, both for shear and for ball viscosity at the same time. It's still relatively common in the field to use constant et al. Rest, constant viscosities when you compare with data. And we actually did some work in Duke last year. It's a paper we published earlier this year, Stefan Bass and I, where we were trying to understand how you can relate. Let's say you find an effective viscosity that can describe your data. How might this viscosity be related to the real temperature-dependent viscosity? And I don't want to spend too much time on this because I think I'm running a little behind on time. But the bottom line is that we could find an expression like this, but only for much more simplified hydrodynamics. So if you have to assume that you have only 0+1 hydrodynamics, which is in a sense the zeroth order approximation for heavy ion collision. And in that case, we could find a relation that depends on the true, so your effective viscosity will be a function of the true viscosity that is temperature dependent, but also will be dependent on your equation of state through the speed of sound. It will depend on the initial energy of your system. So if you start probing your system so if your system has a higher initial temperature, it will see a different viscosity than if it has a smaller temperature. Now, the two take-home messages of this were, first, that anytime you see an effective viscosity, it's obviously some combination of a true viscosity and some dynamical details of your fluid. So you expect, for example, this effective viscosity to be different at shear and at the LHC. And we try to quantify it, although for relativistic calculation, we did manage to extend this to 1 + 1D, but for full 2 + 1D simulation, this is quite challenging. The other thing to remember is that an effective viscosity will never really, at least from all the work that we did, you will never really be able to mimic properly a temperature-dependent viscosity with a constant one. Now you can model possibly enough details, the details that matter. So it's a bit of a subtle question. And there's recent work by Fernando Gardim and Jean-Yves Litro about this. But just a word of warning about constant effective viscosities if you see them in the literature. Now, again, back in the days, they were doing this because they were basically the first one to do this kind of analysis. Now, the other challenge that they realized was that this viscosity depends on other details of your model. So, for example, here, they used two different initial conditions for their hydrodynamics, two different models. And they found that the viscosity that you extract is different depending on this initial condition. And we know now that this is a general feature, that to model a heavy ion collision, you really need to model all these different stages of the collision. And your viscosity only enters here, but depending on how you model this stage and this stage and this stage, you will change your viscosity. So it's very challenging to extract the viscosity because it depends on everything in the problem. And there's a number of different models that are being investigated for all these different stages. Now, the result I will show use a specific choice of model that so for the initial condition, we chose, by initial condition, I mean both the collision itself and this pre-equilibrium phase, we chose what is essentially a parameterized model. So you have a model that can have that can describe many different possible scenarios of initial conditions. And you vary all these parameters. You vary the size of the hotspot that you deposit in the collision. You vary how much energy you deposit, the kind of the profile. And you vary how long you wait for this initialization before you start the hydro. So we have all these different parameters. And the fact that we have, here we have 7 parameters. There are 2 here. So we have 7 parameters to describe these initial conditions. And it's completely a reflection, as the question was asked earlier. It's completely a reflection of our currently limited theoretical control of this phase of the collision. So if you don't have good theoretical control, a thing that you want to do is include all the physics that you can, but what you don't have a good control over, you can vary the parameters, which is what we did. We also have 8 parameters to describe, so 4 each for the shear viscosity and the ball viscosity. And again, we're trying to constrain a function. And we use what is known, again, from theory to try to get some understanding of what kind of function we should use. So you want something flexible enough to constrain, to actually be able to describe the shear and the ball viscosity of QCD. But you want you want to guide it with what is known about it. So here we use this slope at low temperature, a slope at higher temperature. We have an inflection point, and we vary this value at the inflection point. So we had a very flexible parameterization of shear viscosity. And ball viscosity, we have very different parameterization, which again is inspired by theoretical calculation. which suggests that ball viscosity would have a peak around somewhere in the deconfinement region. So we varied the value of this peak, the width of this peak, whether this peak is symmetric or not. And what we do is to calibrate all those parameters against the data and see which one is favored.
JF, can I have a question there?
Sure.
Yeah, so what is the difference between this free streaming time and the formation time that you might have in order to start the hydrodynamic picture?
Right. So free streaming time is exactly the same thing as the installation time of hydrodynamics.
Oh, okay, it's the same. Okay, all right.
Yeah. Any other question at this point? All right, so the challenge that we have is that we're not trying to do what is done here, which is given a viscosity, what do we predict for the observable? We want to do exactly the opposite. We want to ask, given the observables, what is the ensemble of viscosities that are consistent with the measurement and with the uncertainties from the measurement? And this is where, I'm sure you've heard about this before, this is where Bayesian inference comes in. So Bayesian inference is you're trying to find the model parameters that are consistent with a set of measurement. That's something in general called the inverse problem. You can use Bayes inference as a solution to this inverse problem. And what you do is essentially you treat the data as probability distributions. And really, I mean, this is not a stretch because data are probability distribution in most cases. You're averaging over events, so you have a mean and you have a certain statistical uncertainty, so you have a normal distribution. Now, for systematic uncertainty, there are more subtleties about thinking about this as this year probability distribution, but I think in general, it's a relatively straightforward concept. Now we do the same thing for the model. We said that the model's prediction are probability distributions. And you should understand it this way. Whatever you do, your model will always have some numerical uncertainty and some statistical uncertainty often, because we can only, for example, average over a certain number of collisions. And you should account for this uncertainty in your analysis when you compare with data, which is what we do. And this Bayesian inference will combine the probability distribution from the data and from the model to provide probabilistic constraints on the viscosity. So you're not looking for a value or a mean, you're looking really for a probability distribution for your viscosity. And in practice, we make the same general assumption as people who often do Bayesian analysis do, which is you assume that all your uncertainties are Gaussian, are normally disputed. And what you end up is your posterior, which is this probability distribution you're looking for, is given by basically it's basically minus e to the minus chi-square over 2. So you have the mean value of your measurement, you have the uncertainty of your measurement, you have the prediction of your model, you have your theoretical uncertainty that also enter here, and you have the so-called prior, which is how you enforce certain condition on your parameters, such as positivity. You can have causality constraints. And what you do is simply compute this posterior given a model and given a set of measurement. So the result I'll be showing in the next few slides are from this actually very long paper that we released, that JETSCAPE Collaboration released last month. Derek Everett from Ohio State and Weihao Ke from originally Duke and now Berkeley were really the driving forces behind this paper. I was one of the convener of the working group behind this work. So what we did is first we calibrated, so we used the model that I just described, and we calibrated against a set of measurements we compared with a set of measurements from the LHC, 2.76 TeV. So the measurements that we used were charge hadron VN, mean PT fluctuation, identified hadron mean PT, and various hadron multiplicities. And the lines that you're showing here is how well we can describe this data. And there are multiple lines, because those lines are, again, I mean, or constraint is not a single value of the parameter. It's a probability distribution. So what you do is that you sample this probability distribution and you compare with the data. So you can see that we can describe all these measurements well, and we obtain these constraints on the viscosity, on the shear and the ball viscosity. Now, let me already skip. This is not our final result, so let me already skip to. Let me make a few other points before I show in later slide the final results. The first thing to remember is that, again, it's a probabilistic constraint, which means that you shouldn't look at the middle of distribution and say that, well, that's probably what the ball viscosity is, and that's probably what the shear is. There's a wide range of different samples that you can draw from this distribution that have very little to do with each other. So just remember this, probabilistic constraints. The next thing that we did was to, at the same time, calibrate on measurement from the LHC and from RIC. So we used a smaller subset of measurements from RIC just for technical reasons. So we use identified hadron multiplicity mean PT and charge hadron V2. And we saw a small, and because we don't use very much data at RIC, we didn't see a large shift in part because we don't use a lot of data. We didn't see a large shift in the preferred value of viscosities when we added this data. Now, it's still interesting. It's very interesting to see that we can describe almost all of this data simultaneously, which is not trivial. And I also want to highlight, maybe an odd thing to highlight, is that there's also observables that we don't fit that well. So we have some tension with the kaons. And to us, actually, it was, I wouldn't say relieving, but it was interesting to see, because some people have a worry that once you have enough parameters in your model, you can describe anything. And it's clearly not the case what we have. I mean, we have a large number of parameters because it's difficult to constrain temperature-dependent function, and you have a lot of uncertainty initial conditions. But it's still a finite, there's still a finite set of data that you can describe. And it's reassuring that we get somewhat consistent constraint from both RIC and LHC using this model.
Jean-Francois, I have a question. Looking at the bulk versus shear viscosity, two things. One is, for me, one is are the units directly comparable? Meaning, if a lot of the, at least initial hydro models, ignored bulk, saying that there's very little, if any, bulk, except maybe at the transition time. But, does this tell me that there is still significant bulk compared to shear, or how do I compare those two graphs to start with?
They are not directly comparable. There's some numerical factor, depending on exactly what kind of gradients you have in your hydrodynamics. There's some numerical factor that go in front of shear and bulk. If you have, for example, 0 + 1D hydro, I think you would compare Z/S with 4/3 of Et/S. So it's similar, but again, it depends on, if you have other types of gradient in your medium, you may have a much bigger effect of shear than bulk, even if you have the same numerical value. So it really depends on the type of medium that you have. But I would say yes. I mean, for the longest time, people have assumed that ball viscosity is very small. And I don't think we have evidence with this. And to be fair, this is not our final result. I'll show an updated result that include theoretical uncertainty in a few plots. But we don't, at the moment, we don't believe that ball viscosity is neither negligible nor small. It seems to be an important ingredient in heavy ion collision. Yeah, and doesn't seem to be as small as people thought in the past.
You know, I frankly was always surprised thinking that, you know, the system should be expanding in a way where you must have some bulk viscosity. I mean, the whole expansion process, regardless of whether it's quarks, gluons, or hadrons. But anyway, go ahead. Thank you.
And I'd also say, I think in the past, many people have set bulk to zero for simplicity as well. I think there was a mix of assuming that bulk was small, and also it was convenient to start with only one of the viscosity.
Yeah, sure. Or even no viscosity at the start. Okay.
Yeah, exactly, right. So this is not our final result. And the reason it's not our final result is that we wanted to investigate certain model uncertainty in our analysis. And these results were emphasized in this shorter paper that was also put on arXiv last month, or 2 months ago. We just submitted it to PRL. And the idea is that there are other parts that are not parameterized right now in our model that we almost know for certain have a certain amount of theoretical uncertainty. And the fact that you get a value of viscosity given a model choice doesn't mean that this is the correct viscosity. It simply means that it's the viscosity given your choice. So what we did was to investigate this uncertainty. And to better understand this uncertainty, just think of this transition that we have to do from hydrodynamics to particles. So at some point, you have to stop the hydrodynamics because your medium is too dilute and a collective hydrodynamic description doesn't make sense. The problem is that hydrodynamics is a coarse-grained description. It doesn't have information about how many pions you have, how many kaons you have, and what's the energy of these pions, kaon, proton. It only tells you what is the total energy, the total momentum, for example, of your fluid at a given point. Now, if you make simplifying assumption, like you assume that you have ideal hydrodynamics, then you solve your problem. Because if you have ideal hydrodynamics, it means that you have exact local thermal equilibrium in your fluid, which means that these momentum distributions have to be either Fermi, Dirac, or Bose-Einstein. But as soon as you turn on viscosity, it means that you have some deviation from you have some viscosity in your system, you have some local deviation from equilibrium, which means that you'll have some deviation from Fermi, Dirac, and Bose-Einstein of your momentum distribution. So what you need to find is how to map properly these deviation, the bulk pressure, the so-called bulk pressure in your shear tensor, which characterize how much you deviate locally from equilibrium. You have to map this to how much it modifies your hydrodynamic momentum distribution. Should you pump more energy into pions? Should you send it into heavier resonances? And you have all these different models that are used commonly in the literature. You have this 14-moment approximation. You have a certain solution of a Chapman-Enskog using the relaxation time approximation. This is a different model that has been investigated at Duke. And what we did was, short of knowing exactly which one is the best description of what happens in QCD, we can simply try all three models and see how much it affects or constraints on the viscosity. And you can see here the result. So the blue is what I've been showing up to now, which is the grad 14-moment approximation. And if you change this, if you use a different model, so if you use this Chapman-Enskog, you have this red dashed line here. And if you use this Duke-based viscous correction, you have this green line here. So you can see that you actually have a fair amount of uncertainty coming from this. And it's important to quantify it, because if you don't, it means that you're biasing. You can have very precise extraction, but it's a biased extraction of your viscosity. Now, I want to emphasize, it might not look like a big uncertainty, but you always have to compare with the prior. So the prior, I haven't said too much about it, but it's essentially the range of viscosity that you allow your model to explore. You always have to restrict it to a finite range. And how much you have, so basically how small is your posterior compared to your prior is what you learn from the data. So what you see here is that your prior and your posterior, so the gray is the prior and all the other ones are posteriors. They're very similar to the prior. So at high temperature, you're not learning so much about the shear or the ball viscosity. It's only at lower temperature that you are. And I'll come back to this. We have a nice plot of this in a few slides. Now the question is, which one should you use? If we knew, if somebody managed to derive some first principle argument that, for example, grad is a much better reflection of what happens in QCD than Chapman-Enskog RTA, then you simply use the blue line and you say, that's my best guess for the viscosity of QCD. Now, we don't have this information right now. We don't really have evidence to believe that one is better at describing QCD than the other one. So an alternative that we can use is to simply let the data decide. So you look at how well these different models can describe the data. And if one does better, you should give more weight to this one. So here I show a summary of different, so it's essentially how much the model prediction minus the experimental data over the uncertainty of the data. So if you're between -1 and 1, you're within 1 sigma of the data, and so on. And you have these results for different observables as a function of centrality. And you have also this result for these different choice of model between your hydro and how you sample your hadrons from your hydro. And it's actually hard to see from this figure. So we used a statistical quantity that's called the base evidence, which really is the normalization of your posterior. And the evidence has nice property. It rewards a good fit to data, but it also rewards simplicity, which means, I mean, in our case, rewarding simplicity is not important, but just remember that you'll always get a better fit to data if you keep adding parameters. So it's good to have a quantity that both gauge how well you fit data, but also how many parameters you're using. So it's not really a chi-square per degree of freedom, but you can think of it as an analogy, I think. And there's more information here. There's a very nice discussion in this paper if you're interested. Now, if you look at this evidence that really quantifies how well we agree with measurement, you see that actually the green and the blue are much more favored by a factor of 1,000 than the red. And it's not obvious from these plots. And it's really that the red has trouble fitting the proton to pion ratio. And I have to emphasize again, we only use the protons at the LHC because at RIC there's some worry about the measurements. So we're a little hesitant to use the data. And simply one of our model has trouble fitting this proton-pion ratio. And the result is that we think if you want to use the data to pick one of these models, you should give a very small weight to this red band, this red constraint on the viscosity. And using the evidence, you can do something that is called a Bayesian model averaging, which is simply you average those different curves weighted by the evidence, by this number. And then you obtain the orange band that is shown here. So that is our final result for, at the moment, what we think is the best constraint on the shear viscosity of QCD and the ball viscosity of QCD. And we added here this information gain, which is just a way to quantify how much information you have in your posterior compared to your prior. So in a sense, how wide is this one compared to this one? How wide is the orange compared to the gray? And you can see that at very high temperature, we actually don't really have very much information. So we're not saying that bulk is large here or that bulk is small here. We're saying that we really don't have the information to tell using our observables. And the same here. We can't really tell, what is the value of shear viscosity at 350 MeV. But we have decent constraint at lower temperature, and we get values between maybe 0.08 and 0.2, which is also typical of what is found in the literature. And for bulk viscosity, we do exclude small values of bulk viscosity. So at least using our model at the moment, we have very good evidence that we have a finite bulk viscosity.
Sorry, just a question. So how do you quantify this information gain here?
It's the so-called Kullback-Leibler information entropy. So it's, in a sense, I think you're folding two distributions together and you see how much they overlap. And if they overlap perfectly, you have zero information gain. And if they don't overlap, you have a large information gain. I can send you more information if you want. It's relatively simple. You can do this for any probability distribution. So it's a relatively simple numerical calculation to do.
Okay, thank you. And the other question, although I don't know if it's a valid one, is you have this like prior and then you go to your posterior. So are you like already say pretty confident that within your confidence level that the distribution of the true value is going to be within the prior? I don't know if that's a valid question or not.
It is. So the one thing you don't want is your posterior to bunch up at some corner of your prior.
Mm-hmm.
That would mean that most likely you didn't use a wide enough prior. Now, that's not the case. When our posterior actually is constrained, it seems to be comfortably within our prior. And when we're close to the edge of our prior, it's basically when we have no constraint at all.
Mm-hmm.
Yeah. So, but actually, it's one of the things that I think other fields are more used to Bayesian analysis, like in cosmology. I think they have much more insights in the choice of prior. And this is something that will have to be studied in more details in our field as well.
Okay, thank you.
But in this case, I have a sort of a follow-up question. If you, for the eta over S, if you would widen your prior distribution at higher temperatures, does then, let's say, the posterior remain where it is at now, or does it then fill up again?
I suspect it would fill up. I mean, it's a complicated question because there's also a limit where if your viscosity is too large, you can't even trust your hydro. So the other scenario you don't want is, even if your prior goes to a high viscosity, you wouldn't want your hydrodynamics to favor a very high viscosity, because essentially it's your model that would favor values of a parameter that are somewhat at the limit of its regime of applicability. So that would be a red flag. Yeah, I suspect that here, I mean, eventually it's going to cap, because I don't think that, I think if we had very, very high viscosity, either we wouldn't be able to fit the data, very high viscosity at high temperature, either we wouldn't be able to fit the data, or honestly, we wouldn't even be able to trust our calculation. So at some point, that's also where the prior becomes useful. It's, do you even want to run your model where you don't trust your model? So you need this balance between informed decision from the data and informed decision from the theory. Yeah. All right, let me wrap up by just saying, probably you're aware of this other extraction of shear and bulk viscosity that was done in Duke actually 2 years ago. And you may notice that the result is actually quite different between here or ball viscosity and what they obtain. We have, if you look in our paper, and if you look in this paper, and actually the longer paper, we have a extended discussion on why we're finding different results. And part of it, and a big part of it, appears to be the choice of prior. So the choice of prior was not shown here, but our understanding is that the prior actually hugs very much this region. So essentially, what was shown here is not that ball viscosity needs to be small, but it's that if you assume that ball viscosity is small in this region, your posterior will simply fill this region as well. So they used a much stronger prior than we use in the analysis, which is, as far as we understand, why you have such a big difference between our results. There's also some small modeling choices as well that change the result. But in the sense that the results are consistent in the sense that at high temperature, we don't seem to have any constraint on ball viscosity beyond what we choose for prior. So if you have good theoretical reason to simply cut off ball viscosity at a certain value, you should do it. We were a little concerned about this in the new analysis, so we broadened the prior a lot, and we did see that we don't have so much constraint on ball viscosity at high temperature. All right, so I had more slides on photons, and if anybody's interested after, I can give them, but let me wrap up here by just saying, this is the analysis we made. This is I think it's really a state-of-the-art extraction of a shear and ball viscosity. If you look at our long paper, we've been extremely careful actually about validating our model, really understanding well the weaknesses and the strength of the Bayesian analysis. And really, it's not that these distributions will not change. Really, our work was to build solid foundations so that we can look at additional theoretical uncertainties, we can add data, and we can, as we systematically add this information, we can really constrain the viscosities and trust our results, because we've been, I think, very careful about how we read the results and how people should read our results as well. So let me stop here, and if you have any question about photons later, I can discuss this as well.
Yeah, thanks a lot for your talk. So let's go to a few questions. I also have some questions myself, but let's open the floor also first to someone else. So
I'll ask a question, JF. So I've been thinking about this large kind of uncertainty at high temperature. That reminds me of a lot like the gluon PDF uncertainty at high X for some reason, right? So there they said that in order to reduce that uncertainty, you have to do jet measurements at forward rapidities, and you have to go to higher PT, or you have to go to different, flavor space. And so in this case, what do we have to do to get a better handle on the high temperature? Because that is before you're getting much smaller in time, might be even before thermalization, not thermalization, but the initial temperature, right? So what do we have there?
Right, so that's where, for example, photons could play a role, or others, other observables. It's a difficult question, because some of you might be aware there's been a Bayesian analysis recently by people at CERN and by people in the Netherlands, and they find a much smaller ball viscosity as well. And what they did was to use, for example, PT differential data. They use also PLED, and so they use more measurements, and they obtained a very different result for the ball viscosity, very similar for shear, but very smaller, much smaller for bulk. And when we saw this, in a sense, we were not surprised, because we're not saying that you can't constrain ball viscosity well. We're saying that when you constrain when you try to constrain your shear and your ball viscosity, well, you have to consider many factors at the same time. So you need an observable that depends strongly on the viscosity, right? So it could be that PT, a virtual observable, depends strongly on viscosity, which is excellent, right? You can constrain viscosity. You also need something that's easy to measure and has small uncertainties. Also, I think PT differential observables can.
Right.
I mean, you also need something that doesn't depend too much on aspects of your model that you know are still under investigation.
Right.
And I think that's the problem. It's not that we don't know how to add the data. It's that if you go only in one direction in this axis, you might end up in the wrong corner. This is the right corner, right? This is, you have precise and accurate. If you have precise but not accurate, you will get a very good, you'll get very narrow value for your ball viscosity. But as you add data, this value will, jump around.
Yep.
As you change your model, this value will start jumping around. And it's risky, especially risky because people will look at these values and start wondering if you should trust any of these calculations. So that's why in our own analysis, we really try to emphasize more the journey than the result, because we still think that this is a conservative result and this is the best we can get. But we really work hard to introduce for the first time theoretical uncertainties in our calculation and be much more thoughtful about validating the entire analysis. And that's how we are more confident about our analysis. And I'd say it's different from what they do like CTEC does, or what they do in PP, because I think in PP, I think you have a lot less worry about theoretical uncertainty. I think the foundations are much stronger than in our field. I think, I don't know if that's fair. That's my impression, that you may be more measurement limited than you are from the theory.
Right.
Does that make sense?
Yeah. No, I think it's definitely fair to say that we are experiment driven in most sense.
Yeah. I think the usual answer to your question would be, for example, you certainly expect, for example, photons to be more sensitive to early stage. And, as Mike said earlier, photons certainly a favorite topic of mine. And I think they are excellent probes. The problem, again, for photons is that you have this, you have both large theoretical uncertainty and large experimental uncertainty.
Yeah.
So they're not the first thing. So I think they're excellent at better understanding our model. And they're really helping us pushing our understanding of heavy ion collisions. But in terms of calibration, it's harder.
Yeah.
So Jean-Francois, I've got a question. Speaking of earlier times and photons, and next I want to ask about heavy flavor, not so much at earlier times, but what happens if you add, charm and beauty to your quarks in your plasma? What happens in terms of the equilibrium? And for example, if one were looking at low momentum or energy, heavy flavor particles, is that something you've looked into, or what do you think about?
It's not something we've looked into. In theory, we'd have the know-how to, and I have to emphasize, again, this work was done, it's not obvious why it was done in the JETSCAPE Collaboration, who's really more focused on hard probes and
Right.
heavy quarks. But in a sense, we're trying to side by side, on one hand, study the soft sector, so the mostly light hadrons, and on the other hand, there was efforts to do the same thing on the hard probe side, and we're actually hoping that we can merge those efforts and actually constrain better both the viscosity and the Q hat of charged hadrons at the same time. I don't have any specific insights. I mean, I'm sure they would help. And I think I think the theory of heavy quark energy loss is relatively mature. So it would be a region where you would have good theoretical control over what's happening. So you could really make good use of the data, actually. So I think it's not something we're investigating right now, but it's something we're thinking about in the future.
Okay, but you're talking about heavy flavors and, more the initial stage are hard probes. And I'm just wondering about, lower momentum B and D quarks, B and D mesons, for example, where, Alice in the next run will take much higher statistics and go down in momentum.
Okay.
So given that, I'm sure you will end up adding heavier quarks to your equilibrium, but do you have any insight into what that might do?
So the short answer is no. One thing we know is that looking at heavier hadrons, at soft, soft heavy hadrons, depends heavily on this uncertainty that we quantified here. So this uncertainty that we quantified, which were these different models that I've been plotting here, right? So essentially the heavier your hadron, the less of an impact it has on your energy momentum tensor, because they're heavy, but there's not many of them. So it becomes quite difficult to constrain so essentially your prediction becomes very model dependent when you transition from your hydro to your hadron. So how you sample those additional hadrons, is that what you're asking?
Yeah, but also now that we're talking about it, I'm assuming you don't have even the strange quarks in there, or what?
We have
so heavy.
So you mean, for example, lambda or?
Yeah, well, the strange quarks in the equilibrium model.
Yeah, no, I mean, okay, we do in the equation of state.
Okay.
So we have the strange quark in the equation of state.
Okay.
I think there's debates whether you should include the charm in the equation of state. I mean, it's been done, but whether you should actually, I mean, the odds that charm quark can actually thermalize in a heavy ion collision are a little low. So it's unclear how you should deal with that. Right. So we did not include the strange hadrons at the moment because we know that they have a large dependence on this, and I would assume that the hadrons you're discussing about will have the same issue. Yeah, I mean, in a sense, it's good to add them because it's a test of our model here as well, right? So as we said, one of the models is disfavored by a proton to baryon ratio. It's good, the more hadrons that we have, the more we can tell if one model is really systematically preferred to the others. And that would help, actually. So in that sense, having this improved data would help, yes, at this level. And the effect on bulk, I'm not exactly sure, but it would certainly have some effect.
Okay, thanks.
We have a raised hand.
I'd like
from
to
Nicholas.
ask a question,
Yeah,
if I may. First of all, I want to mention it was a nice talk and informative.
Thank you.
So I have a question about some aspects of things that might come out of your model. So I understand that you start from macroscopics and you have a sequence of models you use for different stages. And I think you should be able to answer my question based on your model. So the question is about what happens in the hydrodynamic stage. What sort of flows are actually occurring in the model system? Are they very much laminar flows? Is there basically nothing, no flow? Is it laminar? Is it turbulent? What's happening?
Okay, so essentially it's an explosion. You have it's mainly an expansion, and you don't really have, I mean, you have Yeah, I don't think you have the more exotic type of flows playing a big role. It's really mainly a 1D expansion that becomes a 3D expansion. You probably have some turbulence, but that's still under investigation.
Yeah. Well, I mean, if all you have is expansion, I don't think there's any shear. So shear viscosity won't even come in. Is that correct?
Well, I mean,
It's
it plays a
literally
role.
a uniform expansion.
Right. So it plays a role because you start with something that's very much 1D, and that becomes very much 3D. So the shear plays a role in this.
Oh, so it's not a three-dimensional expansion. It's some sort of anisotropic expansion.
Yeah, exactly. Yes, exactly.
Okay.
So it's slowly driven to a 3+1D expansion. Actually, it's slowly driven to 2+1D expansion. Where's my?
Yeah.
But certainly you have, especially at early times, you have a lot of shear actually, because you have all those gradients, all those gradient differences in the flow that are coming from these fluctuations at early time. Now the shear is still relatively large actually at later times. Let's see.
So trying to understand your response to Nick, is this really because you have pressure differences in the different directions that you have to shear?
So at this point, it's because you have.
I mean, you have different flows in the different directions, so it's not like an isotropic explosion. And
No,
so
yeah,
I would
no, it's
think
certainly
you
not
get shear there.
Yeah. I mean, it goes towards a cylindrical expansion in a sense, right? So, so you're slowly averaging out what's happening in the transverse plane. What's happening in the other direction is relatively independent.
Okay, but that would be the sort of spatial average behavior. But on small scales, there may well be a lot of shear or rotation going on and viscosity playing a role. I mean, the thing is that if viscosity is small, and I don't mean viscosity ratio to entropy density, I mean viscosity. If viscosity is small compared with scales of your droplet, plasma droplet, then you'd really expect a lot of turbulence. I mean, if the Reynolds number is large or something like that.
I think so. The Reynolds number. So the Knudsen number has been quantified, and it gets relatively large actually. The Reynolds, it's okay. It's also.
Sorry, which number did you say?
The Knudsen has been quantified, and it's relatively large actually. Mm-hmm. Reynolds is basically for example, just to make sure we mean the same thing. So Reynolds would be basically a ratio between your bulk pressure, for example, and your energy density, or the ratio between your shear tensor and your energy density. That should be an estimate.
Well, the Reynolds number involves inverse viscosity, and it involves lengths and velocities.
Okay, I think it's right. I think it's the opposite. So it's a ratio of the energy density over your bulk pressure, for example. Is that right?
I don't know. I'm not in this field.
Okay, I see. I can take a look and send you more information if you want.
Okay. Yeah. I mean, I always sort of bring up this question because it may play some role in claims about what the viscosity works out as being, particularly as the viscosity is claimed to be very small. In the sense of eta over S being small.
Right. So the entropy is huge, though. So the viscosity itself is quite large, actually.
Yeah. Okay. Thanks.
Okay. Sure.
I have a little bit more of a photon-related question. So you've shown a few plots where you have the eta over S as function of the temperature, But what then about it's all connected a bit, but what then about, let's say, the temperature as function of time, and then also related to the experimental observables that we can actually obtain. So for example, if you take a thermal photon spectrum, you can fit it and you get an effective temperature, right? But how difficult would it be to, let's say, unfold or use a model prediction to go from the effective temperature that we can actually measure to, let's say, an initial temperature of your plasma? Like,
right. So
is
in a
that doable?
sense, so the I don't think I added a plot of the photon spectra to my talk, but so in a sense, already from hadronic observables, you know what your temperature distribution is, simply because you use this multi-stage model. You have a phase that is described with fluid dynamics, which means at everywhere that you're using fluid dynamics, you can define a temperature. And so, for example, here the temperature is around 150 MeV, here it's 200. And so already hadrons constrain the entire, well, not the entire, it constrains a large fraction of the temperature profile. Now, the thing that hadrons might not be sensitive to is what's happening at early time. So you could have very many different scenarios at early time that would lead to similar evolution at later time. So that might be where photons could play. That is where photons can play a bigger role. And I have, if you scroll down the slides, I have this, a summary of ongoing work on photons. And there's been something like 20 papers on the early stage of heavy ion collision, how to study them with photons over the past few years. So it's one of the very hot topic right now. Now you have to be very careful how you read this slope that you get from the photon spectra, right? Because honestly, most photons are produced here. Most photons are not produced here. So low PT photons are produced in this large space-time region of relatively low temperature. And much fewer photons, harder photons, so higher energy photons are produced at earlier time, but there's not so many of them. So when you fit that slope, you actually mainly, it's photons that are produced at later times, but they are produced from boosted quarks and gluons and hadrons. Here it's really hadrons, right? So they're produced from boosted distribution of hadrons. And it's this combination of the boost and the low temperature that gives this higher effective temperature. Right? So this, 300 MeV or 350 that is extracted at Yale HC is this reflection of the combination of the essentially kinetic and potential energy that you have here. Now, there's probably a connection. I've always dreamed of being able to relate, because the fact that you have a high velocity here and a lower temperature is, of course, related to the fact that here you had very low velocity, but much higher temperature. So you have this kind of conservation. You have obviously conservation of energy. So there's probably some connection between the effective temperature you extract here and the effective temperature you have at early times. But you have to be very careful. Not to read too much into that temperature. There's a lot entering in it.